Hello all, it is the official start time of the meeting. However, Glenn, our lead chair for shepherding this, is currently having audio issues, so he's trying to sort that out, and we'll get going in a little bit. In the meantime, while he's working on this, if anybody is eager to jump up and take the role of note taker, we'd love to hear from you.
This is Barbara. I can help with notes.
Thank you so much, Barbara. You can use the Cody, of course.
But of course.
Yeah.
Oh, we hear Glenn now.
Awesome. That's progress. I can now hear you and you can hear me. Excellent. 1 second with the slides in. I had to do a reboot.
I had suggested to Glenn in chat, have you tried turning it off and back on again? So apparently the IT still works.
All right. 1 more second here. Be ready. Sorry about that. I logged in. I couldn't hear audio and I couldn't send audio.
I'll mention also that while Glenn is still doing this, if anybody is not microphone enabled and would like to bring something to the mic, it's easy enough for me to just jabberscribe without having to find another volunteer to do it. So I'll keep an eye on chat, and if you preface your line with Mike, I will know that this is something you want said to the group.
All right. Can everyone see the slides at this point?
Yes.
All right. Then shall we get started, sir?
Please do.
Okay. Welcome everybody to ADD, session number 1 at IETF 109. As you are aware, all IETF sessions are covered by Notewell, so we are as well. We have a pretty simple agenda today, but I think it's going to fill the hour very nicely. We have the blue sheets, which I guess are now automatic. We have scribe selection, which sounds like it's been taken care of. We've displayed Notewell. The agenda bash I'll do in a second, but we essentially have a presentation to start off with by Tommy Pauly, who has a 0-0 draft to go over. There's a bunch of material in this 0-0 draft, which will talk about the concept of equivalent resolvers, which is something that was introduced by draft box ADD requirements. So what we'll do is we'll do the presentation by Tommy, and then we'll do some basic questions. But the meat of it, this concept of equivalent resolvers, we'll have as a separate discussion after that draft is presented. And that will probably take most of the hour. And then we'll have a very quick, at the very end, 5 minutes, probably not even that, quick discussion about session number 2, which is a 2-hour session scheduled for this coming Friday. So I'll open up any additions or changes to this, or removals, changes to this draft agenda. Okay, moving on. So I'm Glenn Dean, one of your co-chairs, and David Lawrence is my other co-chair of ADD, and our area director is Barry Leva. Tommy, are you on the line? You're muted,
Hello.
Tommy.
All right. I think the audio just takes a while to connect. Can you hear me now?
Oh, we can. Let me switch over to your slides. Give me 1 second here. I had this all nicely set up before I did the reboot. And of course, the reboot threw it all away. All right, there's your slides. Let me know when you want me to go to the next slide, and I'll just sit back, and you're in the driver's seat, Tommy.
Sounds good. Thank you. All right. So what I'll be sharing today is a simplified proposal that some of us, the authors listed here on the slide, have worked on since our previous interim meeting. And we've called this proposal DEAR, the discovery of equivalent encrypted resolvers. And this is largely reflecting the scope that the working group seemed to want to take based on our interim meeting discussions of saying, let's just have a very simple use case in which we want to discover the equivalent encrypted resolver for a network, given that I already know an address. As the chair has mentioned, we'll need to go into more details on what equivalent really means and what are the guarantees we get from that. Does it actually give you any security properties or any trust properties or not? But this proposal hopefully can give some concrete details that help us think about one way that this discovery mechanism can work. Next slide, please. All right, so what are equivalent resolvers? And that's, again, something that needs to be discussed. The way that we initially defined it here, we essentially had two options, and we talk about how to address both. One is when there's a very simple case in which I have another DNS protocol that's available on the same IP address, on the same server. So this is saying I got provisioned a particular IP address and I can speak DNS over TLS to it, but I can also speak DNS over HTTPS. There's some degree to which this may be viewed as equivalent. A stronger version of this that's authenticated is when we can have some certificate that claims ownership over both of these, such that I could actually have two different IP addresses for my resolvers, but have some level of proof that these are related or managed by the same entity. Next slide. All right, so in this draft, we define two different use cases that we're trying to enable discovery of encrypted resolvers for. The first case is when you already have an IP address of a resolver, generally a unencrypted DNS over port 53 resolver, and you want to discover what is the one or multiple equivalent encrypted resolvers I can access for this. And this address could come from a network provisioning protocol or be typed in manually. It could just be essentially saying, I am aware of 8.8.8.8, but I don't know if it supports dot or do or how to get to those. Tell me about those pieces of information. The other use case is one in which you already know the name of an encrypted resolver, but you want to discover the properties of that resolver, like what are the port or the URL path for DO that you need to access, and essentially what are the lists of the different protocols that it does support. One thing that we specifically do not cover is any type of discovery of non-equivalent encrypted resolvers, such as some upstream resolver that may not be able to be covered by a common certificate or share an IP address. Next slide, please. So the mechanism that we discussed using for discovery is based on a draft that Ben Schwartz wrote up for describing the properties of a DNS resolver in a DNS record itself. So he wrote up how to use a service binding record, an SVCB record, to list out essentially alternative services that a resolver offers. So in this case, we can have a DNS server, for example, .NET, and we can get different records, one that indicates that it supports DOE using HTTP2 and has a specific URI template. And then I can also have an indication in another record that says it also supports .dot, and maybe it has an alternative host name that it's using, .example.net, and it has a specific port it's running on. And this can be expanded to support DNS over QUIC or any other future protocol. We're kind of relying on that as a separate document and really just talking about how to apply it for a discovery use case. Next slide, please. So for the first use case, when we have an IP address and we essentially just want to upgrade from unencrypted DNS to encrypted DNS, the IP address, as I mentioned before, can be provisioned in a number of different ways. It can come from the network, such as over DHCP or RAs. It can come from a VPN protocol. It can be entered manually by the user. Each of these different use cases or these different provisioning mechanisms has different trust properties. Maybe you trust DHCP and RA. Maybe you have RA guard on your network, but there's not a lot of user trust in who really is this that's provisioning that information, oftentimes. A VPN or a user entered value may be different, and that may be something that we have more trust in. And so some of the guarantees that we get from upgrading discovery could be stronger. For this approach, the draft defines sending a query for a special use domain name. It proposes reserving something like resolver.arpa so that you do a query for DNS resolver.arpa. And you can get so you send that query to the address of your normal DNS over 53 server. So I can send a query to Quad8, let's say, for this special use domain name, and it could send me in the response one or more answers for equivalent resolvers, which will represent the different protocols that this resolver supports. Next slide, please. For this case, we discussed two different modes in which you can do it. There is what I think would be the preferred mode, which is to have it be an authenticated upgrade. And what are we trying to authenticate here? In this case, we are saying that the certificate of the encrypted resolver that we end up connecting to must include the original IP address that we knew about, Quad8 or whatever else it is, in its subject alternative name list, along with the name of the resolver itself. And this mode should absolutely be required if the IP address is different, because otherwise we have no way to prevent a number of attacks that would allow an attacker to divert encrypted DNS traffic to themselves. It also came up on the list in a discussion with Ecker that you could also require the SAN to cover the IP address of the encrypted resolver itself. That's something that we had discussed and thought about before, but we're not sure about the threat model and if that's something that we needed to cover. But that's something I think we should discuss. The other mode is an opportunistic mode in which you aren't able to cover anything or validate anything in the certificate itself, the draft recommends that this mode only be used when the IP address of the encrypted resolver is identical to the one of the unencrypted resolver, so that essentially it is, as far as you know, the same entity that you're talking to. This is a, I want to use encrypted DNS because I think it's better than nothing, but it's not proving anything about how much you should trust that entity, other than saying it looks like the same person you would have been talking to anyway. Next slide, please. So the other use case is discovery using a known name. You may already know a resolver name for a couple different reasons. One, we may be defining new mechanisms to provision a resolver name. You could add the name of the resolver to DHCP, RAs, it could be in a PVD, it could be in a VPN configuration item. If we go down this road, this allows us to not put all of the details about DO and DOT or DNS over QUIC into DHCP options directly, but only have them define the name of the resolver and then use further DNS queries to enumerate all of the DNS details afterwards. The name could also be something that's entered manually. Being able to enter a resolver name may be simpler than having a user type in a full DO URI template. It's also an interesting use case if you have an encrypted resolver that you know about, but you can't access it. So maybe the ports for DOT are blocked, but you want to discover if there's an equivalent DO resolver when you only had DOT configured before. Next slide, please. So in this case, we don't use the special use domain name, but instead we can simply do a query for the resolver name that we already knew about. So this is really just using Benchworth's document kind of as is, but explaining kind of how it's used in this deployment. And in this case, the certificate must cover the originally known name. In general, that's going to be the same thing, but it's possible that, let's say, DOT server has a slightly different name than the DO server. Any certificate would need to cover both to prove that it's really the same equivalent resolver that you're accessing. Next slide, please. So that's the proposal at hand. If there are any questions about the mechanism, I'd like to hear that. And other than that, I think this can be a good starting place for our discussion about equivalency.
Yeah, so the one thing I'd ask is for people to keep their questions focused on everything except for the concept of basic equivalency. That we're going to have an extended discussion after this. So.
Please. Hang on. Yes, I am managing the queue, but I don't have the buttons at the moment that are. Oh, I just enabled my.
You just have to tell them to unmute themselves. You just call them up and they'll unmute themselves.
Okay, well that was it then. Eric, please. EKR.
Yeah. So thinking about this name version as opposed to IP version, it seems like it has the same problem that I mentioned with respect to the IP version, but is not fixed by the same fix, which is to say that if you don't trust the resolution of that name, then the attacker can redirect themselves through you. They can redirect you through themselves, thus controlling your source IP address. Is that correct?
Okay, so let's say I know, well, okay, so I know like DNS.Google for DOT. I learn about its DO properties. I connect to DNS.Google with DO now. In that case, it sounds like that's an attack that could happen regardless of the discovery mechanism, that just trying to reach out to the DNS server by name, the encrypted DNS server by name has that problem regardless of any extra discovery.
Yeah,
If
I
I
think that's
wasn't already
correct.
provisioned with a hard-coded IP address.
Yeah, I think that's correct.
Yeah. Yeah. So I think that's just kind of a more general property of not kind of having a hard-coded address along with your encrypted resolver name.
Okay, thank you. Martin Thompson, please.
It takes a little while, doesn't it? So I'm really not very clear on why you have multiple reference identities when you seem to have a clear reference identity. So if you've discovered something through, for instance, DHCP, and the DHCP is giving you an IP address, then you look for an IP address SAN, right? And that's all you need. If you got DNS.Google, then you look for DNS.Google in the certificate, and that's all you need. The draft seemed to say something about multiple reference identities, and that was very confusing to me. You kept talking about having extra names or something, and then there was an extra name that you would get through the Service B record, for instance, and then you would validate that as well as the IP address.
Oh, I see. So, right, in this case, you would be, let's say, yeah, the DHCP gives you quad 8. You look up quad 8 and it says, I have a DOE resolver, which is DNS.Google/DNS query. I think it's just saying, kind of by default, your SAN should cover the name that's in the URI. Like if the URI you're accessing has a name in it, you're validating that anyway. And in addition, you should validate the IP address. I think maybe we should kind of clarify the language.
Please.
Yeah, that's all I was trying to say.
Okay. Yep.
Thank you, Martin. Ralph Weber, please. Ralph is sharing his screen.
Maybe it's the wrong button. Still need audio.
Yeah, we
see you. You need to click on the audio button.
Can people hear me now?
Now we can, yes.
Yep.
Okay, great. Sorry, let me troubleshoot it. So the first question is, I mean, you're talking about the discovery of a resolver, but it is often the case in today's world that people have configured more than one resolver, and one might be upgradable and the other not. Is there any? I mean, how do you want to handle that case? And the second question is the. I mean, private IP addresses we can't kind of have certificates about, but it is a very common use case. Now, if I read the draft correct, it is kind of okay for it to just do kind of, for instance, .853 without checking the IP address. Is that correct on how I understand it?
Yeah. So to your first question about multiple, I think that goes more into how the client would end up, using this information in presence of having some that are upgradable, some are not. We don't get into that here. I'm not sure if we should get into that. We're just talking about the mechanism. And for the private IP address space, the kind of the one thing we allow for in that is the opportunistic mode, which says if you manage to host the same resolver on the encrypted resolver on the same IP address, that's okay. But beyond that, we'll need a new mechanism. And I think.
And there is no checking. I mean, because I'm not sure what you could actually check there, because it's a private IP address, supposedly.
Exactly. Yeah, there's not much to check, and I think there are two ways forward for networks that have like a resolver forwarder that's on a private IP address. Either they figure out how to host some encrypted DNS on that, or we add in something like a name into DHCP or RA that will say, here's the name of the alternate encrypted DNS server that you can go out and reach to.
Okay.
Thank you very much, Ben Schwartz.
Hi. So I wanted to talk about Ecker's interesting observation that an attacker in the network could redirect your encrypted stream in order to make your apparent client IP different from the vantage point of the server that you're talking to, even if you have an authenticated connection to the server. So I think that's an interesting and novel observation, but I think that we should declare it out of scope. And my reasoning is that client IPs are not validated in TLS, so that's a security property of the secured transport that HTTPS inherits, for example. The whole web has the same problem. And DNS over TLS inherits because it uses TLS, and DNS over HTTPS inherits. So I think we should just say that that's out of scope, and if we do want to come up with security protocols that can prove the client IP from the vantage point of the server or something like that, then we should come back to that later. I wanted to agree with Martin Thompson that let's not turn the service B target name into a reference identity if we can possibly avoid it. And more generally, the same IP restriction I think is really interesting. And I've said this, I think, on the list, but I think that the same IP restriction is based on a threat model that I haven't quite heard stated precisely, and that I'd like to get stated precisely somewhere. I think this goes to our next segment discussion about what equivalence really means. So I'd like to think some about that. My suspicion right now is that this comes down to a transient to persistent attack upgrade concern.
Yes. Yes.
Okay, thanks.
Thank you, Ben. David.
Hi, David Skenazy. Can you hear me?
Yes, we can.
Ah, it works. Cool. So I was wondering, and it's kind of more of a 10,000-foot question, but so one, when our team on Chrome was, is working on Do, one of the the techniques we use is kind of like auto upgrading to the same IP, and one of the main failings of that technique is that the majority of users have are configured with a DNS resolver that's in 1918 space. Pretty much, it's your little whatever Wi-Fi router you bought is your DNS resolver. Does this do anything to help us with those devices, or are those considered out of scope for this proposal?
The private address on the local network case, right?
Yeah.
Yeah. So I think the question is, in those networks, how are they adding support for encrypted DNS, right? Because presumably you're trying to find out what is that network's encrypted DNS server. So I mean,
well, no, but that's actually my point is that they're not. The great majority of users on this planet have a router that they don't update the firmware for, and so that's not going to get encrypted DNS. And so is that a problem that you're not trying to tackle? And if that's out of scope, that's totally fine. I'm just trying to make sure what the bounds are.
Right. It is not something that we think has a clear solution that doesn't open up another attack. There are certainly ways that we can update those networks, but it is possible that there are going to be certain routers that if they don't update and they don't let certain options be passed through, that you will not be able to just upgrade them to the equivalent one without having some other provisioning of like the name that you should be using for that network customer.
Yeah, no, just them, because I think this is and will remain the majority of users, and it's like I would love to have a solution for them, but if this isn't it, that's fine. It just means we need to have another solution.
So we're trying to find a solution for anyone, not just that case. And that case seems to have a lot of minefields in it.
Okay, I mean, and that's reasonable. We can start somewhere that's easier and build up from there. Cool, thank you.
Thank you, David. Eckert.
Yeah, so I actually think this mechanism is fighting with that a little bit. So I mean, the semantics of your opportunistic, right, are you say, please go to IP blah, and if IP blah happens to match the IP you have for the resolver, then mission accomplished, you upgrade, right? But the situation that David's talking about, which is quite a common situation, is where the client knows one IP and the server is unaware of that IP. But it's actually the case that if you just connected to that IP, it might not work, right? So I think, I mean, I actually have a question. What happens with these devices if you just connect to like the IP and try to do TLS? I don't know. Do you?
Oh, so like
the choke,
like the router zone.
Yeah, does it choke?
Address?
Yeah.
Yeah, we'll have to find out.
I mean, this is actually an argument, I guess, for DNS curve, right? Because DNS curve theoretically works through these devices.
Yeah, and to be clear, like our opportunistic proposal here was defining what it means to do it opportunistically based on the hint from the special use domain name answer.
Right.
So that is something that could still be theoretically filtered out by a network.
Right. Well, I'm assuming these devices aren't trying to stop you; they just don't care, right?
Right.
Yeah. If they're trying to stop you, it's like game over, right? But
yeah.
I mean, I think the interesting question to ask is there some mechanism? I think, as David says, is there some mechanism where is there some set of cases where where what you have is basically a pretty dumb forwarding resolver to one of the large, to one of the large, resolver farms in the world that would take dot or dough if you had it, and you can talk to it because the forwarding resolver doesn't try to filter the traffic. Is there some way to upgrade dough in those cases? And it feels like it's not quite clear how to do that, but that seems like a problem which is worth working on. We should have chosen in this case to pick some very restrictive threat models, but there was a very restrictive use case model like that. It's really only like one of 10 resolvers. Is there some way to fix the problem?
Yeah, there's one other point with these forwarders. When we talk about the definition of equivalency, I'm wondering, is it true that they would be equivalent to whatever it is? Because if they are a forwarder that is technically intercepting the messages, they often do some level of filtering, or they have some extra override for showing you the page of your router when you load other page.
Yep.
And skipping it would change it. So it kind of goes outside of the definition of this really is the same resolver. And if you want something that is equivalent, you need to change your original resolver. Yeah,
and do you have any data on? Actually for David too. Do you have any data on a fraction of apparent resolvers actually have some 1918 address?
We don't currently have that, but that's something that we don't either. Get. Yeah, it sounds like a worthwhile thing to collect metrics.
And I think the relevant case is, I think, people who don't have some obviously hand configured address like 1111 and also don't have and also have 19 address, are also doing it.
Right.
Okay.
And there are also a lot of networks that do give out, other resolver IP addresses. I think a lot of Comcast networks, their CPs and stuff will give addresses that are not private addresses.
Right. Well, that's the case. That's the thing we shouldn't be. That's what I want to measure. So,
yeah.
Thank you, Eckert. Tiru, please. Your mic is not transmitting. Tiru, are you here? Oh, okay, his mic is coming online.
I think there's some problem with that. Can you hear me?
Yeah.
Hello?
Yes, now we can.
Hello?
Hello.
Hello?
Hello, we hear you.
Hello?
Uh-oh. Everybody else besides me hears him, right? Yeah.
Yep.
But Tiru has turned off his mic. So let's, while he sorts that out, Martin. Oh, Tiru might be back though, so.
Hello?
Okay, can you hear us, Tiru? We hear you. Okay, I'll send him a side channel message.
Yes, Terry, we can hear you.
I'm sending a chat message to him.
Okay, let me reconnect. Sorry, guys. I think there's some problem with audio. Sorry for that. Martin, please continue.
I was going to continue this conversation that Eka and Tommy were having here and suggest that perhaps the case that they're talking about where someone has the 1918 address and the dumb forwarder kind of works in this case, because you make the query to the special use domain name and you get back an IP address and you just connect to it and use .do or .dot or whatever it is that it tells you to do, and we're done here. Because what we're looking at here is a case where you don't have a reference identity necessarily. It does mean that you don't get any of the properties that we might be interested in terms of being able to rely on the DHCP or RA providing something that we might trust with scare quotes, but I think it gets a lot of what we're kind of looking for in the end. So for those cases that I'm interested in, particularly the case where we're looking to say, go to the DO server that's being provided by an ISP outside of the home network, then I think what we have is, this is probably enough for that use case.
So essentially you're saying relax any checks and just say the addresses don't match, but just use it anyway.
You don't have a reference identity in that case, right? And then the question is, what name do you go looking for? And that's a little bit challenging. But you've already started out in completely insecure context with no real trust in anything. So I don't know. It's even weaker than the other model where you accept that the DHCP is secure, but it could work.
Yeah, I think. I mean, we need to consider the fact that it creates essentially an encrypted channel to someone who may be an attacker. It allows them to do that if they can essentially successfully inject one packet to you and trick you. Whereas before, in order to intercept all of your DNS traffic, they had to do it continually. So it's the kind of temporary versus persistent attack.
Yeah. It's not a great position to be in, but it tends to be an option people could take. Yeah, it's certainly an option, and some people may want to do it, some people may not. And so one reason I pointed that out is that we potentially have a context, particularly with our trusted recursive resolver program, where there are certain identities that we might be willing to connect to anyway, and others that we simply wouldn't. And so that gives us potentially a path to doing that sort of thing.
Right. So essentially an alternative way of blessing the results. Say, even if you are lying to me, you're sending me to a legitimate place, so I'll take it.
Yeah, exactly.
Sounds good. Yep.
Thank you, Martin. One of the things I'll note is that we are 40 minutes into our 60-minute session, and this has been a really good conversation, and there's still a couple people in the queue, and could well be another couple. While we did have another item on the agenda about talking about resolver equivalents, that will also probably take a fair bit of time, and so we will just plan on rolling that discussion into the next session. So we're not cutting off, as long as this conversation is still being productive, we're gonna keep this one going as long as it takes right now. So David, please.
Hey, David Skenazy again, Chrome. First off, I want to answer Egger's question about numbers. So these are numbers collected by Eric Orth on Chrome. Apparently, what Chrome sees worldwide is only 15% of users have non-private addresses configured for their DNS. So 85% of users, the vast majority of the internet, is configured with a 1918 DNS resolver. So whatever Wi-Fi router you bought 10 years ago, that's your DNS resolver. Another stat that could be interesting to folks is of those 15%, half of them map to known DOS servers like Quad 8, Quad 1, and so forth. So all this to say, like it sounds like we're building a solution for an incredibly small minority of users, and that sounds like not necessarily the first priority to me. I want to also second like what MT was saying. You could make this, parts of this work by using queries that go through your cheap old router to something that might understand them in the ISP network, if the ISP is willing to stand up DOE. My personal 2 cents is that's, even if that's not properly vetted and trusted, it's still better than what we have today where everything is in the clear. So maybe kind of weakening the security model here might improve user security.
Yeah, that's good. And thanks for the stats on that. That's very useful to have. One option that also comes to mind is we can have potentially different recommendations for what to do when we have 1918 addresses, and essentially allow more loosey-goosey, opportunistic upgrade when you have a private address that can't be authenticated, versus if someone has configured Quad 1 or Quad 8 and making sure that cannot be attacked.
Okay, thank you, David and Tommy. On to Ben.
Hey, so Ben Schwartz. So I've heard a few different suggestions of ways that you could potentially key a loosening of the matching requirements in opportunistic mode. So I heard something about keying that on the basis of whether the IP is RFC 1918. I heard keying it on the basis of whether the encrypted resolver IP is on a list of known nicely behaved resolvers. Another condition that I think could be interesting is if the client knows more about the network that it's on. So for example, if the configuration came to the client in an IPv6 RA, and the client has some way to assess the network and say this network probably does not have RA guard functionality, then that would be maybe another case where we can say there's essentially nothing to protect here, and so we can be more open to redirection.
Yeah, that's a good point.
Thank you, Ben. We're going to try Tiru again.
Hello, guys. Can you hear me now?
Yes, we can.
Hey,
can you hear us?
Thanks for that. Hey,
Okay,
I mean, this draft is a great start. So what we are doing to solve the private IP addresses problem, at least on the routers where we have our security services, what we are trying to do is we are using Acme, where either the ISP or the security provider would give an unique domain name. And then we are using Acme to assign a certificate to that, so that what would happen is that the endpoint would still be able to use TLS with the DOH or DOT forwarder hosted on the router. And then the router still continues to use private IP addresses for serving the encrypted DNS service, but that will be only visible to the endpoint devices connected to the home and not to anybody else outside the home network. But where we are currently stuck at with regard to our draft is referring to using DHCP RA to solve that problem, and we have a dependency on the router to support that. But it's not clear if we move to a DNS-based mechanism for discovery, how would that work, and how would that problem be solved?
Tommy, do you want to?
I don't think I have any particular comments for that one.
Okay, great. So, Tiru, anything else?
No, thanks.
Okay, thank you. Ecker, please.
So, like, I have to admit, I expected the numbers to be not as bad as David indicated. Those are pretty terrible. And I think we really, like, I think in light of that, we need to really go back and ask what we're trying to do here. Because if what we're trying, I mean, if you go back and you say like, it sounds to me like if we're not solving the problem of people who have like 1982 DNSs as a resolver, then we're like not doing very much useful. So, like maybe we gotta go back and ask like how to solve that problem, and then see if that problem extends to other things. But I mean, like I know it's a resolve problem you think you can solve, but I think like if we know that 85% of people like have the problem, some other problem, then we need to figure that problem out. And I think this has been useful to flush that out. But and this is for the chairs. Like we really need to. I think we really need to like, we need to figure out the problem definition at this point.
Definitely agree on that, and we're working toward that. I will note that with Eric's last comments, that was actually the end of the queue, but there's also been quite a lot of active discussion in Jabber. If anybody there this is your kind of your last call. If you think that you've made a salient comment there that should actually make it into the notes and come to the rest of the group, then please step forward. Got another couple of seconds, or I'll hand it back to Glenn. Okay, Glenn, off to you again.
Awesome. Let me show my screen here. Let's see, how much time do we have left? Oh. All right. So the next topic we're going to talk about is equivalent resolvers. And I was really happy to be able to finally use this clip art of apples and oranges. So this is a slide that Chris Box has made, pulling out the definition that is currently in draft box ADD requirements, which is what the Deer draft, my understanding, was based upon. And so we thought that, given that there's some discussion about this on the list, and this is kind of an important sort of discussion point that the Deer draft is based upon, we thought that it'd be really good topic of conversation for us to explore what this group really wants to tease this out to mean. So I'll read, for everybody here. What is equivalence? Given two resolvers A and B, equivalence is the claim that A and B can provide the same upper layer DNS function, i.e. response messages towards the client. This does not include the DNS transport protocol, such as regular DO 53 or DNS over HTTPS or DOT, which can differ between equivalent resolvers. So far, there's been two modes of how you assert this claim of equivalence. One would be network identified, where somewhere at the network level, either through the DHCP or RA, there's this information given out that says, hey, B is equivalent to A, and you can go with that. And then there's a resolver identified, where resolver A says that B is equivalent to it. So with that, I'm going to just open the floor and let people discuss. What is your interpretation of equivalence? Do you see this definition as we have it now as being sufficient and complete? Do we need to further tease out some cases around it? Let's explore this topic, have at it. We'll run this until about 5 minutes before the end of the session, which will then cut off the queue, and we'll pick up this conversation on the Friday session when we have it in the end of the week. Okay, David, I'll turn it back over to you to manage the queue.
Martin, please.
So many permissions dialogues. I had a slightly different thing, but I think this one's mostly okay. So my kind of understanding was, I said, what did I say? I said, whatever resolver you currently have, assume that you got that through means that is absolutely secure, and you can communicate it with it through means that are also absolutely secure. Then, using that information, find an equivalent DOH or DOT resolver that you can use on a completely insecure network. And that's a different way of formulating that. And it still has the same sort of constraints on it in terms of network identification and resolver identification. But I'm moderately happy with this formulation. I can't see anything wrong with it aside from that.
Great. Thank you, Martin. Ecker?
As I indicated on the list, I'm not happy with this formulation, and I'm actually surprised Martin is, because what Martin said is incredibly different from this formulation. Like, this formulation could absolutely include resolver, which gave you the same answers, but posted your responses, posted your queries to Twitter, which surely is not okay. Including one which operated by the attacker. So I think I sent some text to the list. I don't think it's perfect, but I think it's more in the right lines than this.
Is that it, Ecker?
Oh, yes, I just...
Yeah, yeah, okay, thank you. Ben, please.
Hey, so to reiterate something I've said many times now, I think we need to talk about a temporal component here, about whether two resolvers not only are equivalent, but are going to stay equivalent. Because if there's an attacker who in our model can be present only briefly, then I think that changes our conception of what it means to be equivalent.
Yep, Ted, please.
So the point I wanted to make was actually about the response messages. And I think that the concern I have is if somebody tries to test, is this in fact equivalent, by continuing to ask both for some period of time, that the response messages could be different from the two different ones, even though their behavior toward the rest of the domain name system is in fact the same. Just because unless they're actually serving out of the same cache, and using the same mechanics upstream to query the either to forward the upstream resolver or the authoritatives, they can get different answers just because of the behavior of the rest of the system changing over time in ways that is not related to the function of the resolver. So I think we want to be careful about giving a simple test like the response messages you would get from A and B would be the same. I think that the claim that they provide the same upper layer functionality is closer, but much less well defined. And I think you'd actually have to write down what pieces of that DNS functionality are in fact the same in order to get it something that the client could be sure of. And I do worry that most of that is completely untestable by the client. So they're going to get an assertion, but there's no way for them to confirm it, except the response messages, which might give you false data.
Thank you, Ted. Mike Bishop, please.
I just wanted to note that the definition of equivalence that was used earlier was that it is managed by the same entity or at the same IP address. I think this is at least a step in a better direction, that even two DNS servers managed by the same entity might deliberately have different policies and behave in different ways. So the filtering and the non-filtering DNS endpoints, for example, can't be equivalent. But yeah, and there's more complexity than just it gives you the same response right now, because it might not, but it provides the same service. I don't know how better to quantify that, though.
Okay, thank you, Mike. I'll mention now that we are closing the queue. Ralph dropped when Eric joined, so Eric, you'll be in queue. And DKG, please. Jim, you're gonna have to save it for next session.
Daniel Con Gilmore, ACLU. So I want to echo what other folks have said here, that looking at the response messages is extremely weak for the questions that I think we care about here. The reason that we're doing DNS privacy and these other transports of change is that there are a lot of factors beyond just what answers do you get. Ecker pointed out, what about a DNS server that sends to Twitter, that republishes to Twitter? But there are several others. I wanted to point out that latency may be another factor in terms of the cache. Linkability, whether the peer can even link your queries across time, whether the peer requires client authentication.
Hey, everyone. Looks like we had to do a reboot.
Do we have DKG back yet? That was really interesting what he was saying.
I'm back. I don't know exactly where the split happened, but I just wanted to echo, I think, what Ecker and Ted were saying, which is that the reason that we're doing DNS privacy, the reason that we're running into these problems here now anyway, is that there's far more than did I get the same records that we care about when we're talking to a DNS resolver. Ecker's description of something that goes to Twitter, that republishes all the queries to Twitter, is just one factor, right? There's other questions about latency, about the ability of the resolver to do to link the client's queries across time, whether that's with cookies or TLS sessions or whatever, whether the resolver does client authentication, that kind of thing. So I just think that this definition is way too weak to to decide in the context that we're talking about now.
And Dan, I'm going to jump in and pause you right there because that's a great final statement. I don't know if we got it into the notes because I think some of the notes are getting captured now. But thank you, Barbara, because I think everyone's just sort of coming back from the Meet Echo incident. So we're at time, and so I would hope to end this a little bit more gracefully than this. Let me say this. So we're going to carry over this conversation because it's a good conversation that we're having. We can have it on the list between now and Friday, but we're going to pick up on Friday with this topic and this conversation, and with the addition of the material that's going to be, I expect, will be discussed on the list, because now you're all focused on the concept of equivalence and the discussion. So, David, are you back? Do you want any last words?
I am. Well, I would just want to encourage, because I know Chris, John Reed, and Eric were all at Orth were all in the queue. So make a note, please, of what it was you wanted to say so that you can bring it to the next session.
And with that, thank you, everybody, for session number 1. Thank you for the folks in the East Coast United States that are staying up. And we'll see you on Friday and on the list.
Good night, good morning, wherever you are.